NISQ era, you know that we have hardware efforts and we have quantum software efforts, and that's why we call them quantum emulators, because we need to mimic the behaviors of the quantum computing, the algorithms, to test through simulators in order to see how far our algorithm is potential before we are going to apply it into the real quantum processor unit, which is the real NISQ hardware. So nowadays the NISQ hardware are limited by the number of qubits. So but basically the companies, they are doing 50 up to 1,000 qubits. But after that, we need to go to the era of fault-tolerant quantum computer, which is beyond the thousands of qubits, where the quantum error corrections has to play the game there in order to demonstrate that the logical qubits are very advantageous. So nowadays, we are going to focus on the quantum software part, and we are going to focus on the variational algorithm part in the quantum simulations. So there are many applications. A lot of research engineers, they are trying to see application in electronic structure properties, in molecules, in atoms, in high energy, even particle physics. Very recently, a lot of people have simulated high energy particle physics using quantum computing methods, also CO2 capture, also energy spectroscopy, a lot of things. And I just find like this article very interesting for people who would like to read about the useful applications in the NISQ era and why we need to merge AI for quantum computing, because as most of you knows, that AI can also play a game now to help us design very useful circuits, very scalable circuits, and optimized, compact, whatever compressed. We are going to see a lot of circuits in the sessions, and it can help also for the optimization by itself, for the training as well. So that's why it's nice to see the merge of AI and quantum. So beyond the NISQ era, as I mentioned, we have the fault-tolerant quantum computing era. How far the quantum computing, in the fault-tolerant quantum computing, the devices can run arbitrarily long, and they can show a very nice results in a complex and more scalable quantum algorithms, thanks to the quantum error correction method. So if you have one logical qubits, how about you have thousands physical applied qubits in the real fault-tolerant quantum computer? And here is the what happens in 2026, what will happen in 2028 and beyond, to see the real advantage of the quantum computing. So the main difference between NISQ and fault-tolerant, as most of you knows, is that the NISQ are only working in the short, shallower circuit depth. But for fault-tolerant, you have to work in a larger and larger scalable circuits, and that's why the algorithms have to be different, and that's why we are going to focus on the yellow color in the NISQ era, as I mentioned, in the variational quantum algorithms. As an example, why just going back to the theory of Feynman, Richard Feynman, I'm gonna just demonstrate an example in the chemistry problem, for example. So some of people, they don't understand, for example, why simulations taking a lot of time, why we need a lot of memory. So for example, you have benzene molecule, you have 6 carbons and you have 6 hydrogen, then you are going to distribute 42 electrons over 36 special orbitals. And then if you map to spin orbitals, you would need 72 spin orbitals. So thanks to the second quantization formalism in physics, we map each orbital into 1 qubit, and that's why we call it 72 qubits. So benzene molecule, in this basis, it needs 72 qubits. So if you want to compute an exact energy of this molecule, then as you see in the equation there, you need to have the dimension of the Hilbert space is limited by the number of orbitals and the number of electrons. So imagine if you wanted to compute this benzene molecule and to see that the Hilbert space is going to be over millions the scale. That's why you will have a lot of memory you need and a lot of time you need in order to exactly compute the minimum energy of the benzene molecule. That's what we call it exponential wall, because the classical computer are facing the problem there. So propane also is a very interesting molecule. I have seen that people now in the classical computing also, they are trying to compute the exact, which we call it full configuration interaction of the 3 carbon and 8 hydrogen and 46 qubits. So they have done it, of course, but they need about 512 processor on 256 nodes for a total time of 113.6. Imagine now the quantum computer with only 72 qubits once existed. You are not going to have 113.6 hours. You will need few seconds to compute exactly the minimum energy. So how far is this nice to help the computation of larger and larger molecules? And that's the main challenge, for example, in quantum chemistry nowadays. I hope now the image is clear for people to know how the quantum simulations are important in terms of computational costs and time consuming. So in this session, we are going to focus on the variational quantum algorithms. So variational quantum algorithms, they say that any trial quantum state, psi theta, the expectation value of a Hamiltonian should be greater or equal to the exact energy. If you sandwich your Hamiltonian and then you have to find the exact energy, this is the way how the variational principle can play a role to find the approximate wave function and the approximate energy or exact energy. So that's why a lot of systems, chemistry and physics, we need to solve the molecular Hamiltonian problem. And that's why we need to apply them as a hybrid approach. The classical computer will help us to the optimization and the quantum computer to represent and compute the expectation values of the Hamiltonian. So from now into up to half an hour, we are going to see the state of the art of variational quantum algorithms in the NISQ era. What are their impact real world problems in the near future? And then we are going to focus on the quantum chemistry, which is very interesting for most of you, I'm sure, to see how the state of the art of the methodologies of the quantum computing for quantum chemistry are important nowadays, and what are the resource estimations in the CNOT gates, in the parameters, and whatever the needed conditions for executing variational quantum algorithms. So let's move now to the state of the art of the variational quantum algorithms. As you have seen, we have a lot of families, right? So we have VQE, variational quantum eigensolver, QAOA, quantum approximate optimization algorithm, VQD is the variational quantum deflation, SSVQ is the subspace variational quantum subsets variational quantum algorithms, eigensolver algorithms family, and the quantum machine learning. So you see there are a lot of plenty of types also of each family. You have also, let's say you have children, right? It's like you have a lot of types. And in fact, a lot of types have different versions. So here I'm showing examples. But imagine since 2017, these algorithms have shown a lot of promising results. And they have been applied, some of them into real quantum computer like IBM or Quantinuum or whatever, IonQ, and they have shown promising results. The problem nowadays is the shot noise, that the number of times the circuit has to be executed is really statistically making errors. And also the Hamiltonian decomposition, also how to decompose the Hamiltonian is very also interesting problem now. The scalability also, it's a number of qubits, how you will cleverly reduce the number of qubits. The optimization also, how faster you are going to find the minimum energy in a very quick way. So that's why you see a lot of versions. And thanks to researchers over all the world, they have shown a lot of new methodologies. We are going to see them in the quantum chemistry applications. So in the next session, we will see each algorithm, how it works, of course, in a very nice way. The pros and the cons. So let's start with the variational quantum eigensolver. As most of you, this is a hybrid. It uses the classical computer and the quantum computer. So here is your gates, here is your qubits, you register them, and here is your circuit, and here is the measurement. What happens is just like your optimizer update the parameters, and then it will feed them back into your quantum parameterized gates. And then once you feed them, then you define your states. And after you measure the Hamiltonians, once you measure, then the classical optimizer update the parameters back and forth until you get your minimum energy. And as I have shown that the measurements is very important there, and the quantum circuits is very important. That's why it's important to find very important methodologies, clever methods, how to reduce the number of measurements, how to scalabilize also the quantum circuits, and how to define chemically or physically inspired ansatz that can be very well defined in the NISQ era. So the pros and cons, of course, the most important thing in the quantum variational eigensolver is that you don't need a fault-tolerant quantum computer. You can apply it in the NISQ. It's a hybrid design, so the classical computer can help you to optimize the parameter. So this will help to reduce the resource demand from the quantum computer. And it can tackle chemistry problem and some optimization problems. The cons is that I would say it's mostly because of the noise. As I mentioned, the statistical noise coming from the repetition of the circuit when executed many times, then it's gonna make a lot of noise, and this is the thing which we call it shot noise, and that's why it's a little bit noisy here, and we need to find a way how to remove this noise through error corrections. And of course, the one of the thing is that you have to know that it can be in terms of the circuit depth also have to be very well defined once you enlarge the number of qubits, and this is of course all the system you are tackling, then the VQE can tackle a lot of problems. So there are a lot of families nowadays in the VQE. I would say there is, for example, the classical VQE, as most of you knows. There is for adapt VQE, we are going to see like gradient-free adapt VQE is very interesting algorithms, and this is basically just different from the different classical VQE is that you only optimize local operators, and so you don't need to make an over optimization in multidimensional parameters, and that's why scientists there, they have find a nice way how to locally optimize one parameter, so you don't need to optimize a lot of parameters in each iterations at the same time. Handover iterative VQE also is very interesting because it's an iterative method, so you don't need a black box circuit, then you are able to in a way learn from each measurements you do per iteration, then you can learn how to update for the second iteration, and in this way you are going to inspirely construct your wave function from the pieces of the Hamiltonian more than just in a heuristic way, like in a random way. So the fragment also is very important for the fragmentation of big molecules. A lot of people like to divide the big molecule into small fragments, and then you apply VQE into different fragments, and then you combine at the end the energies, and you say this is my total energies. Qubit VQE is a kind of, instead of using the qubits, then you use the qubits, and here the NISQ device will be super happy because you will need less number of qubits and you will need less number of gates. But to make this qubit hard in a hardware way, it's really challenging because it's bigger, like 3 or 4 or 5, depends on the dimension of qubits. You need more than 2 qubits. So many applications have been studied nowadays in pharmaceutical way, of course. And of course, we have, as well as in the chemical industrial way, chemical reactions, energy, and material science. So this is for industrialists. Now let's move to the QAOA. This is a very interesting algorithm. This is working as alternative problem, like you have two layers. You have the cost layer and the mixer layer, what means that you have to optimize the parameter in the cost and the mixer. Now you start with Hadamard gates here because you need to make superposition over the computational bases you have, and that's why you will have a lot of bases at the beginning. But then you need cost Hamiltonian from your cost function, of course, you are from the cost Hamiltonian you are doing. Plus, I mean, in alternative way, they kind of mix the Hamiltonian again, because they want to play over rotational and rotational Z gates and Y gates, and that's why they need to add the mixer Hamiltonian. So this is numerically has been tested. That's why people they add the mixer gates, and it's similar to the VQE problem. Then you are going to back and forth update until you get the cost functions, and then you get your minimum energy and the parameterized wave function. So now we have pros and cons. The good thing is that it can work in a very hard optimization tasks compared to classical heuristics. You see, for example, D-Wave and many others, IBM, they have shown that optimization problems QAOA is playing a big role there. It uses shallower circuits because there are many versions in QAOA now, like adapt QAOA is very interesting to shift a lot of non-important cost and mixer gates, and that's why it's nice to run it on the NISQ device. Now, if your optimization problem is larger, then you are going to have larger depth, and that's why it's really the scaling issue. So that's one of the problem, and that's the only thing I would say. And also, it really depends exactly on a lot of parameters because we have mixer and we have the cost Hamiltonian. That's why we have a lot of gates, and that's why it's like hardware efficient ansatz, in fact. So it's really limited by the number of parameters. So we have adapt QAOA, which means that you adaptively select your mixer Hamiltonians operators, and like adapt VQE, then you are iteratively measure the gradient and you add your most important operators, and then you select your most important operators. Now, indirect QAOA, and we have multi-level QAOA. So multi-level, I would say you can work in qubit, for example, QAA. If you have more than a qubit, you are going to use qubit, and this is a multi-level, or you are going to make a multi-level systems because you wanted to reduce the circuit depth. So there are many families, logistics, automotive, finance, manufacturing, and energy. Again, I'm not going to focus on the industrial applications, but this is most important in the application part for QAOA. Now, variational quantum deflation. And the variational quantum deflation is a very interesting because it's aiming to find not only the ground state, but also to find the excited states. How you do that? You just have to add in the top of your cost Hamiltonian, you have to add some penalty term. Once you add the penalty term, then you are going to penalize your cost Hamiltonian, and then you are arriving to the excited state you are going to target. And during our simulation, like Pinelin here, they did a very nice algorithm in VQD, and I think people, if they want to understand, is the best version how to understand VQD. So the penalty term is really important to define the next excited state you want, and you can choose whatever you want, what excited state you wanted to target. And then it will work like the VQE problem standard where you optimize and you minimize. Now, we have pros and cons. The pros is that not like VQE, you can go to excited state, shallow circuits, and there are not only working in ground state, you can work also in application like for materials, because in materials and electronic structure properties, you don't need only to focus on the ground states, you have to go to the first and second and third and fourth excited states. Now, there are many cons, and it's important to, the penalty terms is adding additional cost because you have to measure. So there are additional costs here. And we have also noise because of the additional states, because you are targeting not only ground state, but also the excited states. And therefore, the total measurements is really important to know that it's going to be overheaded. There are many also versions in the VQD. So we have the standard, as I mentioned. We have the weighted VQD, and I would say the weighted VQD is just kind of the word weight. It means that you are adding weight more into the state you want to target in your cost function, the loss function. So if I say the weight is 50, for example, as an integer number, into adding it on top of the first excited state, then this is 100, for example, for the second excited state, because the more you weight it, the more you are going to oblige your minimization to go and target these local states you are going to target. Charge preserving VQD also, it means that in the penalty term, you are going to add, for example, particle number, that, for example, if you are working in ions, then here you have to be careful because you are going to work in the charged era, and then you have to see if you are in a singlet or doublet or triplet, and this is also important to add the spin symmetry as well. So not only charged preserving, but also you can say you wanted also symmetry preserving as well. Subspace research VQE, and here I would say this is a kind of subset of computational basis set you are going to initialize. Let's say you are going to focus on a few inputs, and then due to these inputs, you are going to find the ground and the excited states. So what happens here, you are going to apply VQE normal, then through the orthogonal subspace basis sets, you are going to have multiple eigen states, but they are using the same black box circuit. And in the cost function, you are going to add these terms, the expectation values, and then you measure. So because he knows the previous ground state or the previous first excited state, then the second excited state will have information to be training, and that's why you are able to get simultaneous eigenstates at the same time. So the pros and cons is that indeed it's efficient because you don't need to repeat optimization like VQD, and it's only one box, as I said, because you are going only to optimize one black box optimization parameters, and it will find multiple state at the same time. Cloud application like VQD in excited states and spectroscopy. Now the cons is that it's not so easy because I tested it, for example, by myself, and I find that sometimes it's not easy to find near the cost function which you are going to target. How you will train your parameter is not so easy. So you have to play a lot with the we call it beta parameter in order to target the excited states. So there are many versions. There is the standard, the weighted, and generalized. So what I mean by weighted is again like you add weights. So you can gradually add weights. For example, the ground state, no weights. For example, for the first excited state, you add weight 10. Then about second excited state, you add 20 or 100. So you have to add them, increment them per states. And generalized SSVQE here, it means that you are going also to add symmetry constraints there or particle number conversations in order to apply immediately your target states as well. So we have a lot of applications. A lot of people can work on that. Now the quantum machine learning. So in the quantum machine learning, we have a lot of things to say. So it's using a parameterized circuit, of course, because it should be trained in order to classify the data by the optimization of the loss function and compared to the true data. And that's why this is important because there are many applications also with it. And it's important to train your circuits. And once you train it, then it helps you to predict once you add more new features in your trained circuit at the end, then it will help you to classify the correct output and readout. And that's why it's important because it will predict the new data, as I mentioned, using trained circuits, and the circuit learns to classify the data correctly. And this is why it's important, a lot of application neural network added in the quantum machine learning in order to use the variational quantum principles. So there are a lot of problems and a lot of advantages. So I never tested it yet, but it's a new work. And the thing is that it's very powerful because it leverages quantum power for feature space, hard to access classically, of course, and it's really having a potential for high dimension pattern recognition. So especially once we increase the number of qubits and the number of data set we wanted to encode. And the cons is that there is noise, as you know, and still experimental. So that's why it's still having a lot of cons there. And of course, it's heavy because you have a hybrid, so you have to optimize and you need to require a lot of large data sets. So that's why it's heavy resources needed. So there are many types, and here there is the support vector machine. A lot of you have seen about it, quantum reinforcement learning, and variational quantum autoencoder. So I would advise each one to, once I share the PowerPoint, you can have a look at how they are doing. So I share the references as well. So they are very interesting for pharmaceuticals, for medicine, to know if they are the medicine toxic or not toxic, for example, for the defense, also for manufacturing, accelerators. So it's very important for the quantum machine learning. Now, let's, after that, move to the resources estimations of the state of the art of the models. And here we have, as you've seen, a lot of algorithms, as we have mentioned, from VQE to quantum machine learning. So we have a lot of tests. For example, here I'm showing the following. So I'm showing the type of the algorithms. We are showing the maximum number of qubits has demonstrated in this type of algorithm, the circuit depth, and the maximum gates, and the largest problem solved, for example, using these algorithms, and the references and the quantum application they are can be solved by these algorithms. And for example, if we can see QAOA family, for example, you will need 40 qubits in order to have, with 5 circuit depth, and maximum you need 40 gates. So you see that the more you are increasing the qubits, the more you need gates, and the more you have depth. So I'm just demonstrating here examples how quantum NISQ devices have been applied. I mean, using these kind of algorithms with some statistical and estimation of the resources. So if you are interested, you can have a look with the publications and you have more read about that. Of course, these are not the latest state of the art. There are many other algorithms with less number of qubits and more achieved results. So this is only an example. Of course, for molecular simulation as well, we have seen a lot of molecules. And for example, C2H4 here, it needs 28 qubits just in the minimal basis set. And the accuracy is not so high. So it's achieved, but it needs still a lot of methods to go to the exact energy. So here you need to find a ways how to test them. And here I'm putting the experimental or simulation parts in if they are experimentally tested or they are simulated in the quantum processor units using the simulators. And here you have a lot of types of molecules. So for example, you have chain of hydrogens. So you have, they separate here 2 rings, 5 hydrogen there and 5 hydrogen there. And here it's the way how they saw that they exactly match the FCI using the experimental trapped ionic quantum computer. So I love this article very well because they used a very nice way how to get the minimum energy using 20 qubits. And also, there are many others, people working in the differential propane and people working in drugs, lithium hydride. So you can check each molecule, for example, how much qubit it needs, how much accuracy has been arrived, and what are the state of the art. Did they arrive to the exact energy or they have approximate energies? So now let's move to the quantum computing for quantum chemistry. So quantum chemistry is one of the most promising applications, as you have seen in a lot of social medias, a lot of research. And here we are going to show what are the methodologies to construct and to implement a wave function on a quantum computer. So many researchers have shown a lot of new versions, new methods to show the best efficient quantum circuit, how to compactify the parameters, how to compress the excitations, how to do that. So we are going to see in the next slides. So in the chemistry problem, I'm going to focus on the solving problems in the electronic structure methods. So I'm going to work only in the electrons, how they are correlated and how we compute their energies. That's why we call it electronic structure method. So why classical computational are slowing? As you have seen here in the figure, there in the vertical side is the accuracy, and here is they have the computational cost with the number of the electrons in your system. So for example, density functional theory and the QMC, they can work very well at very small size, for our very large size problems. the DFT, but the accuracy is not so high, right? That's why you need more and more methods that can adding more and more excitation, like triple and double excitation and even quadruple excitations, until you find your exact energy from the Schrodinger equation. So here we have small size, medium size, and great size. And that's why you need to have medium size molecular. You need to apply MP2 and configuration interaction, single and double, and the couple cluster. But of course, if you wanted to compute the full configuration interaction, then the computational cost, as you have seen in the helper space in the first slide, they are going to have a lot of uh, dimension to a lot of determinants, in fact, to add, and then that's why we have a lot of memory to add. Therefore, we need to find a way how to arrive to the FCI with larger size as well, but there is a classical limitation, and that's why the quantum computer is gonna help us there. So now for the unitary couple cluster families, single and double. So now we are going to focus only on the single reference state. We are not going to work on the multi-reference state. If you are interested in the multi-reference state, I have some slides so I can share them later to see what are the current quantum chemistry for quantum computing methods using the multi-reference state. So our focus is gonna be on the single reference states. So how it works, as you have seen in the top here, the wave function is exponentializing the the excitations with their Hermitian conjugates, and then we have applying this exponential on the top of the Hartree-Fock state. And therefore here, this is very interesting because you apply all your fermionic terms, and then you are going to say, I have a lot of properties nice, like chemically inspired, because I just mapped the molecules into fermionic excitations for the electrons. It can be applied on our NISQ device. They are very good for chemistry and they are variational. So we need few parameters in order to do that. So that's why nowadays there are a lot of applications how to compactify this wave function, because the more you enlarge your molecule, the more you have to add excitation. Therefore, the more you have to add parameters, as you can see here, to optimize. So imagine you have only single and double there, and that's why you will need a lot of excitations for larger molecules. Imagine for beryllium hydride, you have 6 electrons over 14 orbitals there. So over 7 spatial, which is mean 14 orbitals. And imagine symmetry here is not so easy. When I did this work, for example, by myself, I tried to add triple excitations on top of the double excitations. And I know that is going to be the depth gonna be more and more, but we need to test how chemically is going to be inspired, how it will work. I mean, in a statistical way. I mean, the emulation simulation way before applying it to the real quantum computer. We know that, but we want to see how the symmetry can cooperate with the additional excitations. That's why I did these triple excitations, but we added particle number, total spin, and the spatial orbital symmetry, how to use the properties of the group theory in order to reduce a lot of parameters. And that's why it's a way how to shift a lot of non-important excitations and therefore maintaining the chemical accuracy you want. But of course, whatever double, single, or triple, you are going to trotterize your wave function. You are going to cut the summation of the exponential into product of exponentials. And therefore, here you have also trotter errors, as you see 1 over t, and you have decomposition, but people normally take one order decomposition. But if you are interested in more, then you are going to have better accuracy, but you have deeper circuit. As you have seen here in one single trotter decomposition, if I map my Hamilton, my wave function, my operator, I am going to end up using the C0 staircase method. I'm gonna up with 6 C0s here only for this exponential of theta Z0, Z1, Z2, and Z3 using the Qiskit language here. Imagine if you have single, then you are going to at least bound it by 4 C0s. And as I mentioned, C0s are very important nowadays, are critical in the NISQ device. So we need to find also compactify way how to reduce the CNOTs. So therefore, you have to reduce the number of operators at the beginning in order to reduce the number of CNOTs. So if you have double excitation, then you are going at least to be bounded by 16 CNOTs. Why? Because you are going to have 16, because you are going to have um, uh, 4 uh, double excitations, but because of the Hermitian, then you are going to have 8. And then here, because it's scalable by 2p minus 2 with the length of the excitations, then you are going to have 16. You have to have 1, 2, 3, and 4, and then 5, 6, 7, and 8, and then another 8 for the first double excitation with his Hermitian conjugate. And that's why it is important to know that the more you add excitation, the more CNOT you are going to have overheaded. Chemical accuracy and strongly correlated systems. So I'm not going to work about the weakly correlated system now. A lot of algorithms have been tested in weak uh, correlated systems, like for hydrogens or lithium hydride or whatever. But if you want to work in a strongly correlated system, what I mean, like when you are going to stretch a lot your bound length in terms of 2 molecules or 3 molecules, the dimers or whatever, and at the same time, it will be strongly correlated because once you have a lot of electrons in your distributed in your orbitals, and this is why we need to compute these dynamic and static correlations in order to add them on top of the energy of the Hartree-Fock. So how about going to beyond the double excitations? Triple excitations is interesting there because it can cover these missing energies in order to help the strongly correlated system be saturated with a well-defined minimum energy. And I have seen some results here. I have done some work in adding triple excitation. We published them. And we have seen in the right here, we have applied triple excitation. And if you see the stars in the red, they are going to have better accuracy because in the beryllium hydride, whatever the bond length you are doing, you are going to have more and more better energy by at least 2 orders of magnitude with respect to double excitations in terms of Hartree units. And as you see that beyond 2.5 angstrom, the energy started to be also decreased. The errors is increasing there. Why? I would say because there have been a reason. I wrote it in the article. Because here at this limit of 2.5, there have been mixing of states there between the ground and the excited states. So that's why the wave function wouldn't be very happy to have the optimal energy very easily. And that's why you have a lot of errors coming there. But of course, the reason have been written very well and defined in the article. Of course, also there have been Fedorov and his colleagues have been working in selectively using whatever double and triple and quadruple. That's why we call it UCCSDTQ. And here selectively, so they have using them in a iterative way. Sorry. And that's why in the beryllium hydride, the number of parameters are much lower because they are selective. But as you see, the accuracy is not so high. So I have done some comparison in a later publication with different publications and with different methodologies. And indeed, this is very interesting methods to reduce the number of parameters. But again, they are going to have a lot of computation of measurements because in each iteration they are going to update and optimize. So it's similar to adapt VQE. So suppose you are going to stay in the fermionic type excitation. I'm not talking about now about the qubit excitation work, and you don't need to go to high rank excitation. I mean, you don't need to go to, I would say, to the triple or quadruple or octuple or sextuple. You need just to achieve your high accuracy, not necessarily to be in the FCI, but with a fewer number of Q parameters. So I would recommend to go to the compact ansatz. It's very interesting because in the compact, it's a new strategy, how our colleague Raoul Matra and his friends, they tried to classically kind of compactify the number of parameters And there have been another one which is called compass. In this way, they did a new strategy also, how they compress the number of excitations. And in this way, they compress the number of operators and therefore the number of parameters using a classical pre-screening methods to select these most important and relative operators. So therefore, they compress the parameters without, of course, having bigger and bigger circuits, and it's called compass. And here I did also comparison. In the next slide, you will see the results. So now suppose this, for example, these methods, they have been limited by the synods because they are still fermionic. Okay, so because of they are still fermionic, the number of synod gates is still gonna be large. So then in my brain, I have thought that how can we try to maintain the chemical accuracy, but predicting a new methodology that can minimize the synod gates with a fixed ansatz without adaptively selecting operators and then measuring gradients, and then we have overheaded gradient measurements. Can we make it? Yes. So how in this article, I didn't work in iterative way. It's just only one block wave function. We call it non-iterative disentangled deuterodecoupled cluster. We use here the symmetry and we use the algebra, linear Lie algebra. So what we have done, we pre-screen like in the compass and the compact methods, we pre-screen the strong excitations to have a robust starting wave function. But on top of that, we enforce symmetry on the excitations because we want to smooth the wave function at the beginning to have faster convergence to arrive to the minimum solution faster. We call them robust starters. And these are built from starter of Pauli terms. So you don't need to work anymore now with fermionic. You only work with the Lie algebra of the starter of 2n minus 2 of complete operators. So you only have these operators. If you have 10 qubits, then you are going to have 2 times 10 minus 2. You are going to have only 18 starters. They are enough to complete my wave function. They are enough to define my real Hilbert states wave function. And here there's a method how to work with the full group and with the full set in order to assure that we have fulfilled the condition of completeness or no. Is our minimal complete pool of excitations satisfy this complete pool, this fully group size and full set? We need to add symmetry there because they reduce a lot of non-important excitations. And that's why we need to check 3 conditions: the group size, the separability, that means, and build the Lie algebra in order to see how the separability, how two commutators, two operators, when they are computing the commutation, do they give me the third one, which is the new operator that is also inside my pool of excitations. Once we have them 2n minus 2, I'm gonna have 2n minus 2 of layers. So I start first layer, then I can make periodic series of circuits until I arrive to k layer into making a nice wave function. We call it an IDAC. Indeed, the result is very nice. As you see, as I mentioned, we need a smooth convergence. As you see here, once I use the strong excitations plus symmetry plus Lie algebra, I'm going to have at least the exact energy there in a very smooth way with a very few steps in the optimizer in the beryllium hydride. So many analogic ways I've seen have been done, like people use Lie algebraic classical simulations in QAOA. There have been a paper, they use the dynamic Lie algebra, and it's based on the periodic background of the establishing the wave function in the periodic way. We call it, that's why it's called dynamic Lie algebra. And it's interesting because it's a kind of similar work, but here they use QAOA for Ising models. So how are the results coming from the NIDAC? And here we are going to see that in strongly correlated system, in 6 hydrogens, you see that we arrive to 10 to the minus 12 of accuracy in a very quick way, tested not experimentally here, everything classically. And as you have seen, if I only have using the Lie algebra, it helps me because it will make the operators already ordered. And that's why the no barren plateau problems, as you have seen here on the green line, and it arrived to the global minima in a very quick and fast way. The same thing for beryllium hydride. So symmetry is important. Strong excitations are important for making a robust wave function, and the Lie algebra to maintain the no ordering problems happen there. So the last section about adapt VQE approach. When I say adapt, that means you have to add operators onto your wave function iteratively. To select these operators, you have to compute their gradients, the largest gradient operator or bunch of operators, you add them on top of your wave function, and then you optimize the full wave function in order to get your excitations. Now, what we have a very interesting thing about adapt VQE, that it will have compact circuit, of course, because you only choose the most important excitations. And also, we are going to have as well less number of parameters. And also, we are going to have more accurate for larger molecules. Now, wait a minute here. Yes. So up to the compact now for larger molecules, it's better than UCCSD because a lot of simulation have been done, and also we have problems because we have a lot of gradients to compute there, and that's why a lot of shots sometimes also needed because of the measurement of the Hamiltonian. So it needs a lot of work there to make a very special and unique adapt VQE nowadays. How does the standard adapt VQE works? So you just have to start your state and you operate your wave function as a reference state Hartree-Fock, and then you measure the gradient of all the Hamiltonian. This is the standard adapt VQE. You select the operator and the largest one, then you have to add it into your wave function. Of course, you need to compute the gradient norm of the gradient. You sum over all the derivatives. And if it's less than a certain threshold, then you are going to use it. After that, you are going to stop and terminate your adapt VQE algorithm. So how it works? So we start here with one iteration. We choose the largest gradient. We see if the gradient norm of the total gradients here are less than the threshold or no. If it's not less, then we terminate. If it's not less, sorry, then we continue and we add this largest gradient one and we optimize, you see, all the parameters. Then after we optimize all of them, then we get the minimum energy, and then we go to the second iteration. The same thing, we recompute the gradient, we check the threshold. If not, then we could need to add more and more. That's why it's adaptive way and iterative way. So there have been a lot of references here. You see there are many versions of adapt VQE, and most of them, they are very interesting. There is no preferences, of course, because some of them, they give you very potential chemical accuracy. Some of them, they give you less number of CNOTs. Some of them, they give you less number of parameters. And so still adapt VQE, from my point of view, needs a lot of work. So in this paper, they work in the multi-reference intercoupled cluster. They compare it with the other adapted VQE methods. Mostly people work in the standard 3 molecules in the STO3G basis set, in the lithium hydride, 6 hydrogen, and beryllium hydride. And as you have seen here, the CNOT gates are still high, even at the accuracy 10 to the minus 5 Hartree. So they haven't mentioned anything about the number of CNOTs, the number of shots also, the number of parameters as well. So here it should be very well defined. What is the number of parameters you have done? What's the number of CNOTs? And what's the number of the measurements you have executed and the number of shots? In this way, you are going to complete and make it perfect adapt VQE. So here, for people who are interested, you can see I have done by myself a lot of scales. So how adapted VQE variants they can scale, how the compass scale, compact scale, quadruple unitary coupled cluster scale, and IDAC how it scales. So I'm not going to go through all of these, but you see, always you have to, I recommend that you have to see the threshold you are working, the gradients if you are doing, how much is scaling. As you see in adaptive VQE, you have a lot of gradients, and also parameters, how you scale it, and the number of CNOTs, you have to scale them. The number of CNOTs is also very interesting. So these are very important resources you have to compute in order to see if your algorithm is important and very good for comparison with other previous algorithms. So here is the article, and I have done a lot of testing of estimations. You can see all the captions, details, what it means. N is the number of electrons, the qubits, sorry. The N of S is the number of parameters, how to scale the number of CNOTs with respect to the excitations, if they are fermionic or qubit excitations, or for example, in an IDAC, for example, they are only very interesting because it's only the number of qubits and the number of the operators from the minimal complete pool. And this is why it's very linear. And you see K and P at the end here because it's a linear. So many advices to read. Also, they have tier trees. So I have read it a few days ago, and it's very interesting to make a denser circuit. We have also very interesting work by Raoul Metra and his colleagues. They find a way how to weigh non-iterative corrections. So they work in the error mitigation methods here and how to find the subspace optimization. Even also, they work in a very nice and unique algorithm in VQE. They find a way how to, at the same time, compute all the states from excited to ground state at the same time in a very professional way. Also, a lot of people have been working recently. I have seen this paper. They have been working into reducing the number of shots. And this, I love it because they have reused the Pauli terms from the previous iterations. And this helps them to reduce, of course, the number of steps at the end and the number of iterations. So they basically work in a very nice way how to also complete the variance-based shot allocations. And also here is a nice article how to reduce the number of resources required by adaptive VQE. They use different type of excitations. We call them coupled exchange operators, mostly in double excitations, I have remembered. And they are very well designed, how they really reduce the number of CNOTs and parameters. Also, there are colleagues, they have been working in the chemically accurate quantum computing using the density basis set. And this is very interesting because it can work with different basis sets. And it has shown a very interesting simulation result comparing to the classical counterpart computing classical quantum chemistry methods. Vibrational, also a lot of people have been working in these methods, and also very interesting to study the conversion there. So finally, before I finish in 2 minutes, I would really advise, if some of you are interested in the hands-on projects, how to implement variation quantum algorithms in general, how to learn. We have a very well-documented library. It's called OpenVQA, and it can be shared by our colleagues from the community now, OpenVQA. I'm sure they are with us. You can share the site. And if you are interested, you can join as a member. You are welcome. If you are interested for collaboration, you are welcome. And publication also, we can speak about that, welcome. So it has more than 35 contributors now, and it's very well designed. You can share this link there, and it starts from the OpenVQE, and then it's now going to Open VQA, and then we are going to Open Hybrid, then we are going to Open Quantum, and we have a large community there working in different applications, material science, drug discovery, and machine learning. So we have more than 10 international professors. They can guide the members to help them in an open source work for the OpenVQE. So this is the roadmap. If you are interested, you can contact me, of course. And this is the roadmap of the open source. Now we are in the OpenVQA sector. As you have seen, we have a lot of variational quantum algorithms. So we need to add all of them in the package. And a lot of people now working on it, thanks to them. In 2030, our vision is to go to open fault-tolerant quantum computer to test our algorithms, maybe quantum phase estimations or whatever Shor's algorithm we can move also, not only variation quantum algorithms. And of course, we have open quantum net. And here we have been starting with using evident machine, which is called Captiva. It's very interesting. And I have using it through OpenVQE, and they are sponsoring now our community into hackathons and whatever. Many thanks to interesting colleague from OpenVQA, Mr. Dav. Thank you so much. He is with us now, and he is a core member of OpenVQA Hub. He helped me in the slides. Thanks a lot. And thank you so much. I hope to create a future of quantum computing and success all together. Thank you so much.
Thanks, Haidar, for mass presentation. Dr. Haidar just now talked about the current state-of-the-art variational quantum algorithms for molecular simulations. In
Yes.
the end, he also discussed about the open source packages. There are many young scientists here, Haidar, so who knows? There may be collaboration in the future. Okay, so
Thank you so much.
we now have 30 minutes for our Q&A session.
Yeah.
To participants, you may either post your questions in the Zoom chat or raise your hand to ask him directly. I see some questions in the Zoom chat. Let me read them. Okay. First is a question from Mr. Ledito. By restricting the space using symmetry, how expressive is this ansatz to tackle molecule tasks?
Sorry, repeat the question.
Yeah. By restricting the space using symmetry, how expressive is this ansatz to tackle molecule tasks?
Okay. Well, as I showed in the NIDAC method, for example, in chemistry, for example, we have tried to show how expressive, because as I mentioned, the symmetry is composing of different components, right? So you restrict your sector by the number of particles you are doing, plus you are going to work on the not only the number of particles, but also the point group symmetry and the spin. So when you restrict the sector, then you are restricting the wave function. And here it's very expressive because it doesn't need additional gates, but in fact, it's in the opposite. It will smoothen the convergence better because it will make your wave function knowing the target. Shall I go to singlet or doublet or triplet if I impose the spin sector there? So there is no overheaded costs needed from the symmetry on the wave function. It's the opposite. In fact, it's what we need because it will reduce a lot of non-important physical, non-important physical parameters and operators. So that's why it is there is no loss of expressivity from this symmetry wave function. So it's flexible. At the same time, it will predict a very good chemical accuracy.
So still, the expressibility is still good, right? It's still high, where even though
Sure.
you restrict the space using symmetry. Is that what you say?
Yes.
Okay.
So there have been many articles. I would advise there is a spin adaptive ansatz. This is making the correct spin symmetry sector and is still very expressive, but you have a lot of excitations to add. There is also the projective VQE, which has been by people from Canada. They have been doing with a project to the right sector you want, and it's still expressive. There is the NIDAC method, which I have shown in the slides. It's using the Lie algebra structure, and in this way, it will preserve the symmetry, and it will be still systematically improvable. So this means that the expressivity is still there. Yeah.
Okay. Thanks, Haidar. The next question comes from Dewan. Dewan is one of my group member. Thanks, Dewan. Okay. It seems, okay, let me read the question. When it comes to the design of ansatzes for VQAs, there seem to be two main directions: hardware efficient ansatzes that are relatively shallow and tailored for current noisy devices, and problem-inspired ansatzes such as UCC-SD that encode more chemical structure but require deeper circuits. Is the current research trend moving more toward problem-inspired approaches despite their hardware cost, or do hardware-efficient designs still tend to dominate in practice? So,
very, very nice question. Thanks a lot. To answer clearly, of course, if you are working in hardware efficient ansatz, it's much better. But very rarely you show a hardware efficient talking about physics and chemistry inspired problem, right? So that's why people are trying to focus on the chemically inspired ansatz nowadays to maintain the accuracy. Because at the end of the day, you need your chemical accuracy, right? If you work with hardware efficient and you don't know yourself where you start just by scratch implementing gates, this is only a test. But I think the main key here is to impose symmetry within the gates and to reduce the number of CNOTs. And it will still maintaining the chemical accuracy. So as you have seen in the recent publications, there is compact, compass, there is adapt VQEs, there is many, because people, they find that hardware efficient ansatz are less accurate. And for scalability, they are not going to work well because they will produce more noise and you will need more and more shots in order to do that. So once you define your ansatz very well in a chemical way, what we call it chemically inspired, then you are able to define your problem, like in any problem you do in physics and chemistry in a classical computer. But the way how you intelligently use Lie algebra there to reduce the size of the Hilbert space of the excitations, for example, in the problem, this is something very needed nowadays, is to combine the Lie algebra structure and to reduce the size of your computations in order to make a small scale, and then you are going to preserve the expressivity of the chemically inspired ansatz, for example, or physically inspired ansatz. So yeah, I would say no hardware efficient ansatz, but people call it hardware efficient ansatz if you apply symmetry and Lie algebra. Then here I wouldn't say it's hardware efficient only by one term, because this symmetry and the Lie algebra, they reduce the number of CNOTs. It's a hardware efficient. That means it's compatible with what NISQ devices needs.
okay.
Yeah.
Dewan, are you happy with Dr. Haidar's explanation? Okay, seems okay. Yes, he's happy. And then this is another question from Mr. Latito. I did not read initially the next question. Regarding your Lie algebraic based ansatz, I think your recent paper, Haidar, he asked, since DLA can be classically simulatable, does it also applies to your ansatz?
Sorry, can you repeat the question?
Yeah, I'm also not sure with the question. Mr. Ledito, uh, can you open your microphone? You speak directly because the
Yeah,
LA.
sure.
Sure. Good.
Sure, yeah. Okay, so I just want to explain the DLA means. What I mean is, yeah, I think Haidar understand dynamical algebra. So people investigate that this DLA can be classically So yeah, my question is, does it apply to your ansatz?
The LA, you mean the Lie algebra?
Dynamically algebra.
Oh, okay. For the dynamically algebra, very nice question. If you have seen the article in NIDAC paper, I have written in the conclusion about how to perhaps use the dynamically algebra in an analogic way to combine it to the chemistry problem. So in our case, we use different approach how to combine the Lie algebraic structure with the symmetry. Now, if you want to ask me, should I use the dynamically algebra? Yes, because we have the similar behavior. We are making periodic circuits from the layers, and they are using also periodic ansatz from different layers. But the dimension of the Lie group they are doing is different way because they concentrated in QAOA and in different application like Ising models. Then I thought, how can we use it in chemistry? I didn't get the answer yet because in the Lie algebra for Ising model, you can easily have XX or YY gates, but for chemistry problem, you have long chains of Hamiltonians. So how can I will dynamically inspire this Hamiltonian? So I didn't have yet the common method that can combine the dynamically algebra with the minimal complete basis set complete pool we are doing using our Lie algebra. So it's completely different. And in their article, they use the GSIM, which means that from simulations, they can know how to cover the most excited state and making a truncated and compact wave function using the dynamically algebra. So I haven't used it in my work.
Yeah, so my question actually is more about the classical simulatability of the ansatz. So because DLA can be, yeah, classically simulatable. So, I mean, have you considered this like classical simulatability of your ansatz? Because restricting your Hilbert space, if you restrict too much, then it can be easy to simulate classically, right?
Yes, yes.
Yeah.
Everything here has been tested classically. In fact, I haven't touched yet applying the methods on real QPUs. So, I mean, in our approach, NIDAC, for example, it has been just tested classically. Like just we computed the expectation value of a Hamiltonian using the SciPy library and stuff. So we haven't yet, in fact, tested it on a real quantum computer, I would say. So this is what you mean, right? Classically, it means you simulate it in your real quantum computer or no? So I haven't tested in a real quantum computer.
Yeah, yeah. Thank you, Haidar.
Okay, thanks for the discussion just now, Mr. Latito. The next question comes from Dr. Prihadi. How do we apply VQA, variational quantum algorithms, to high energy physics? This is maybe any idea?
Very nice question.
Because his background, I know him, his background is high energy physics. Perhaps any hints, Haidar?
I loved very much this question, and to be honest, I thought about it, but I didn't have time to work on it later. So, well, VQA can be used in whatever problem you have. If you define your Hamiltonian, if you map your standard model Hamiltonian or your QCD or QED Hamiltonian into a spin representation, then you are just ending up with a variational principle, and in principle, you can compute the minimum energy or the simulation you wanted. So to have a real-time dynamics or to have, for example, energy or ground state, lower energy excitations, yeah, for example, for the lattice of QCD, for example, Hamiltonians, you can use VQA because, as I said, the principle is not only confined for chemistry, it can be for high energy. For example, also for non-perturbative phenomena. Sometimes also you need to have some terms to add, and this is very important for the phase transition. So like in chemistry, you do some properties like for the dipole moments, and so also you do the same thing using VQA for particle physics. So I would say it should be working okay if we map it. And I have seen an article, I don't know if the doctor have seen that, they have also mapped the wave function, the Hamiltonian into a spin representation, into a qubit representation. So then if you are aiming to find a minimum energy of a lattice QCD, for example, Hamiltonians, then I would definitely use the VQA. Yeah, mathematical general problem at the end.
Sure. Dr. Priyadi, Hadian, are you happy with the, or you would like to comment? Okay, thanks. And then the next question.
It's just a question of encoding, I mean, your lattice Hamiltonian and or the model into qubits. And I think, yeah, it would be possible. And I can share an article how some people, they use the QED methods in order to transform the Hamiltonian also from the quantum electrodynamic. Yeah.
Oh, sure. I think Dr. Prihadi will like it, Haidar. He will appreciate it if there is a, I mean,
yeah.
Okay. The next question is from Dr. Sudrajat. He thank you for a nice presentation. He asked you, what is the capability of VQE in treating excited states? For examples, for the calculation of excitation energies and electronic transitions compared to traditional DFT, for example, or time-dependent DFT.
Yes. So, well, the capability is that it can, as I mentioned, there are two potential versions of VQE. We call them SSVQE. Means that you choose your subspace set of operators of sets, and you project your wave function on the computational basis you want to target, or you can use the penalty term for the you add them in the cost function, and then you measure it on the quantum computer to help you to penalize and to target the excited state you want. So the capability, it can find low excited states. I don't want to go to very high excited states with a very good accuracy for small molecules. But to be honest, for large molecules, I haven't seen yet a very great capability of VQE to go to large molecules. So our colleague from Bombay, from India, Raul Medha, has showed that there is a spectrum of a lot of excited states you can draw from VQE, but I think he tested it on a small molecule like H2O or, so or beryllium hydride or even hydrogen. But if you want to go to, let's say, methane or ethane, even with low basis sets, minimal basis sets, then here I would say the capability is not so easy to define it now. From myself, I haven't tested and I haven't seen a real article. If someone can advise us here would be nice, and a very nice question indeed. So definitely the capability is so strong and robust for VQE in the small molecule scale. But for large scale, I would say I haven't seen that yet. Yeah.
Yeah, I agree with you, Haidar. Let me ask. Let me ask one more. Does the V SSVQE, the method VQE methods to calculate excited states, I forget. Was it using UCC ansatz or was it using hardware efficient ansatz? Which one is better, Haidar?
Yes, very nice question. So if you can see on the in the documentation of OpenVQA, we have shown SSVQE tested on a hardware efficient and tested on a unitary couple cluster. And once we tested it in hydrogen molecule, it was working perfectly for both the hardware efficient and for the unitary coupled cluster, because hydrogen molecule you need 4 qubits if you are just working in a linear mapping from fermionic to qubits. But if you are going to a lithium hydride or to 4 hydrogen, then definitely we fail here with the hardware efficient, and we really need the generalized excitations that can able to obtain the excited states. So therefore, it was not so easy to use the hardware efficient ansatz for larger molecules in the SSVQE.
Okay,
Even we added the weights and we sum the energies for different state, it doesn't work.
Dr. Sudrajat, thank you. Thank you, Dr. Haidar. Next, a question from the operator. In QAOA, what methods can be used to efficiently determine the optimal P for medium-sized systems without starting with low P? For example, P equal to 1 until 3 and incrementally increasing it.
You mean P is the depth of the circuit?
Yes, he answered yes.
So the question is, what is the good methods that can help to reduce the depth, right?
Right.
So you need to perhaps to have a warm start in the initialization of the parameters. If you can find a way how to jump into a stronger minimal energy more than the standard one, this is needing, of course, a lower depth of parameters. And it will, of course, avoid a large space of parameters you need to start from scratch. So the initial guess here is very, very important to have a lower cost Hamiltonian and lower mixer Hamiltonian, therefore lower parameters, I would say. The same thing for VQE is very similar in an IDAC. As I showed, if we have a very nice symmetric start, then it will go smoothly. And here it will help the optimizer to find the minimum energy quickly. And therefore it will need less layer. It's the same way, I mean, if you have it's in fact like QAOA, because you are only differentiating by the black box circuit. But if you strongly start with a very nice, well-defined gates with parameters, initial guess in the optimizer, then you are going to efficiently improve your convergence, and then you need less and less number of length of the depth of the circuits. Machine learning meta optimization also have been working there, and people are using the classical machine learning model in order to reinforcement learning to predict the optimal P or initial good initial parameters. This combination can help you to transfer from minimum to minimum in a more jumps, and can save more and more computation without repeating a lot of layers. Adapt VQAOA also is very interesting, and here you have to use it like adapt VQE. I would say they are the same. In fact, VQE and QAA, they are similar. People are just trying to copy and paste, I would say, because they are similar. I mean, but I don't know why people have to say QAA and I mean VQE. I would say they are almost the same object to find the minimum energy at the end. But of course, this will help the adapt VQAA to treat your P, because it will help to truncate the most possible and efficient operators you want from the gradient measurements. You would know how to go into the structure of your wave function, and therefore less and compact wave function, therefore more or less depth you need in your length of the circuit. This will help to balance the cost and the performance, and it will be fully automated in the wave function how to perform and to make less complex optimization, of course. I hope he liked the answer.
Yes, yes. And then the question from Yuga. In the future, when we have a fully functioning fault-tolerant quantum computer, do we still use the VQA?
You mean do we still use VQA once we have the full tolerant quantum computer without any NISQ devices? This what you mean?
Right. So in long-term fault tolerant, do we still use VQA?
Not
That's
necessarily, because the reason to use VQA was only to see how it will be compatible with the NISQ devices, because they are limited by the number of qubits and CNOTs, and these algorithms are very interesting to this kind of phase, which is the NISQ device. Now, if you wanted to move to partial FTQC, here you still need to compare the hybridization, because the nature of the VQA is the hybridization. So you are able to see how the partial fault tolerance is going to show an advantage, or quantum dominance, we call it nowadays, over the classical computer. Now, if I want to go to the fully fault-tolerant quantum computer, here the question I would say, no, I would have quantum phase estimation, or I would have the Grover's algorithms for optimization and a quadratic to show a quadratic speed up. The quantum phase estimation is supposed to also give me an exact eigenvalues, or Hamiltonian simulation with dynamics also to. So I don't need the VQA in this process, but it can be still applied. I mean, especially in machine learning, I would say in the quantum VQA machine learning, it would be very interesting.
okay. Thanks, Haidar, and thanks, Yuka. You guys, Yuka, they are excellent students.
Some people, they use the VQA as a warm start also for the initialization of the initial guess, and then they use the top quantum phase estimation to apply. So this is how the quantum phase estimation is useful for VQA now. The same thing in the future, I would say they will be also needing each other in the same way, how to prove that the fault tolerant quantum computer is also working from the mixing of these two algorithms. So yeah, it will be needed for sure also.
Okay. Dr. Haidar, I believe our time is up. So um, we thank you a lot for your wonderful presentation and for the uh, warm discussion that we may have. And thanks also to all participants. I will close our colloquium today, and we look forward to seeing you again at our next colloquium. Thanks a
Thank you
lot.
so much. Bye bye. Have a nice
Bye-bye.
day.
Bye-bye, Haidar. Bye-bye, Haidar.
Bye.